This lecture is a continuity for the previous one and covers voltage drop and power loss calculations for a distribution system. Remember that, in the previous lecture, we have developed the phasor diagram for the circuit voltages and currents, and that we have found that the voltage drop is equivalent to the product of the line current and the sum of R cos theta plus X sin theta. If we calculate the percent voltage drop, then we divide the previous equation with the phase base voltage. Also, we usually know the cable impedance in ohms per kilometers, so we can also express the resistance large R in ohms as the distance d multiplied by the linear resistance small r. Similarly, the reactance in ohms large X can be expressed as the product of the distance d and the linear reactance small x. Note that since we have assumed that delta is 0, so this is an approximate equation and does not give the exact value of the voltage drop. For the calculation of the exact voltage drop, we have to consider the exact value of delta. Therefore, we can consider that the constant term is equal to K, which is in percent per amperes per kilometer, and rewrite the percent voltage drop as current I times distance d times constant K. Or we can also consider K in volts per amperes per kilometer as given by this equation, and express the voltage drop in volts as I times d times K. This is an example of a table generated for some cables, with different cross-sectional areas, and for different power factors, depending on the type of load and service. For instance, if we consider a cable of cross-sectional area of 50 square millimeters, feeding an electric motor, with 0.8 power factor at normal operation and 0.35 power factor during startup. Note here that the difference between the two conditions is the power factor. Indeed, during motor starting, the power factor is very low because of magnetic flux establishment. During normal operation, the expected voltage drop in the selected cable, in volts per amperes per kilometer, is 0.89 volts. And it is 0.5 volts per amperes per kilometer during motor startup. Let's practice on an example, where we consider the following feeder, with a uniformly distributed loads of 50 amps, spread equally, at equal distance of 50 meters, along a main primary feeder. The feeder is of type 4 core, with 185 square millimeters cores section area, and insulation type cross-linked polyethylene XLPE, and with a total length of 300 meters. We assume a power factor of 0.85. We want to calculate the summated voltage drop at point F, which is the end of the feeder cable. Before we calculate the summated voltage drop at point F, at the end of the cable, we first start by analyzing the problem and given data. We know that the cable is of type 4 core, 185 square millimeters, XLPE, so from the cable manufacturer data sheet, we can find the linear resistance and reactance. To calculate the percent voltage drop, we can use this equation, where the constant factor K is determined by this equation. Knowing that the power factor is cosine theta, which equals 0.85, so we can calculate sine theta, which equals 0.5268. So, the factor K can be calculated as follows, and find that it equals 0.0598% per amperes per kilometer. Now, we can use this factor K and calculate the percent voltage drop at each point on the feeder. Let's start with point A. The percent voltage drop at point A equals 0.0598 times the total current of 300 amperes, times the distance of point A, that is 0.05 kilometers, which yields a percent voltage drop at point A of 0.897%. Now, we calculate the voltage drop across the section AB, with a length of 50 meters or 0.05 kilometers, using the same equation, and we can find 0.748% voltage drop. Therefore, the total voltage drop at point B is the sum of the voltage drop at point A, plus the voltage drop in segment AB, which yields a value of 1.645%. Similarly, we can calculate the voltage percent drop at each point as follows. At the end, we can find the total percent voltage at point F, that equals 3.141%, which is equivalent to a voltage at point F that equals 250 volts minus the voltage drop of 250 times 0.03141, that is 242.147 volts. Now, we will see how we can calculate the power or copper loss in a distribution system feeder. As you know, the power or conductor loss of a circuit can be expressed simply as PLS equals I square R or I square RD, where big R is the cable total resistance in ohms. Small r is the linear resistance in ohms per kilometer, and D is the distance on the cable. We can also express the loss in per unit or percentage of the power delivered by the circuit, denoted by PR, by dividing the power loss in watts by the PR. Note that PR is the receiving end power of the feeder section under consideration. Now, let's take the same example as before, and apply the power loss calculation presented earlier. So, we consider the same feeder as in the previous example. And we first need to calculate the summated power loss at point F, at end of cable. Then we need to calculate the total power at the sending point O. From previous example, the receiving end phase voltage is VR equals 241.147 volts. Therefore, the per phase loss power at different points on the feeder are calculated as follows. At point A, the distance is 50 m or 0.05 kilometers, the current is 300 amperes, so the power loss is square of the 300 amperes of current times 0.129 of linear resistance times the 0.05 kilometers OD distance, that equals 580.5 watts. The power loss in portion AB is calculated as 250 square times 0.129 times 0.05, that equals 403.125 watts. Similarly, the power loss in portion BC is calculated as 200 square times 0.129 times 0.05, that equals 258 watts. And the power loss in portion CD is calculated as 150 square times 0.129 times 0.05, that equals 145.125 watts. We can continue in the same way and calculate the power losses in portions DE and EF. Then, the total power loss in the cable are the sum of all power losses in each portion of the cable, that is 1467.375 watts. Previously calculated voltages at points A to F are listed here. Using these voltages, we can calculate the power taped at all points A to F, as follows. Now, after calculating all the power tapped at each point on the feeder, we can calculate the total power at the sending end by summing all these powers to the total power loss, which yields a total power at the sending end of 63,770.56 watts. Now, let's consider another example of a three-phase balanced express feeder that has an impedance of 6 plus J20 ohms per phase. At the load end, the line-to-line voltage is 13.8 kV, and the total three-phase balanced power is 1200 kilowatts at a lagging power factor of 0.8. We want to determine the line-to-line voltage at the sending end of the feeder, the power factor at the sending end, the copper loss, or the distribution loss, of the feeder, the power at the sending end in kilowatts. We first calculate the phase voltage at the receiving end from the given value of the line voltage. Since in an express feeder, the line current is the same at the beginning and at the end of the line, we can write that the line current IL equals the sending end current IS, and equals the receiving end current IR, that is determined as the ratio of the receiving end power PR over square root 3, over the receiving end line voltage and over the receiving end power factor. That yields a current on the feeder of 62.75 amperes. Using the receiving end line to neutral voltage as the reference voltage, we can express the sending end voltage as VSLN equals VRLN plus I times EL, where all parameters and variables are expressed in phasor or complex form. Note that, in this example, we will calculate the exact value of the voltage drop and voltage at the sending end, and we will not use the approximate equation. We will just use Ohm law and don't make any assumption. To answer question A, we just use the KVL equation of the voltage and replace with numerical values. We can find that the sending end phase voltage equals 9055.22 volts with a phase angle of 4.93 degrees. And the sending end line voltage equals square root 3 times the phase voltage and adding a phase shift of 30 degrees. Which yields to a value of 16,684.11 volts with a phase angle of 34.93 degrees. The phase angle between the voltage and current at the sending end point is determined by subtracting the phase angle of the current from the phase angle of the voltage, which yields a value of 41.8 degrees. So, the sending end power factor is calculated as the cosine of this angle, that is 0.745, lagging power factor. The power loss are easily calculated using this equation, which yields a value of 70.888 kilowatts. The total three-phase power at the sending end is the sum of the receiving end power and the total power loss we just calculated. That is 1270.888 kilowatts. We can also calculate the power using the sending end voltage, current, and power factor as shown by this equation, which yields exactly the same value. Next, we will see the difference between distributing power, with a three-phase system primary line, and double or single-phase lines. Usually, a utility company strives to achieve a well-balanced distribution system, in order to improve system voltage regulation, by means of equally loading each phase. This is also usually done at the facility level. Indeed, electricians should design and install the single-phase electric wiring system in the facility fed by a three-phase main feeder, so that all three phases are well balanced. This is a difficult but very important task, because power and current unbalance cause voltage unbalance on the network, which may affect the efficiency of many three-phase loads. This table shows an example of how to balance the load on the three phases inside a house. For instance, we can distribute the lighting and socket loads equally on each phase. Since the number of water heater, air conditioners, and hand dryers are not a multiple of 3, then we need to balance their power as much as possible and split them equally on the three phases. In this case, since the water heater and hand dryer have the same cumulative power as one air conditioner, then we can have them connected to phase A while the two other air conditioners are connected to the phases B and C. As you can notice, the total power on each phase is the same, which makes a well-balanced three-phase system. Of course, the demand and diversity factors should be taken into account when estimating the maximum coincident demands on the circuits. This figure shows a typical three-phase feeder with laterals that can be three-phase with 3 or 4 wires, or 2 phases with 2 wires, or single phase with 2 wires, or 2 phases plus neutral, 3 wires. All possibilities exist, and this mix of different types of laterals can create severe system unbalance if we don't pay sincere consideration to the load balancing issue. Indeed, at the utility side, usually there are many laterals on a primary feeder that are not necessarily in three-phase. For example, they could be single-phase laterals. This mixing of three- and single-phase distribution system causes the voltage drop and power loss due to load current not only in the phase conductor but also in the neutral wire or return path. For the single-phase system, the current flows in the phase to the load and returns back to the source through the neutral wire. So the impedance of the neutral wire is included in the voltage drop and power loss calculations. While in a balanced three-phase system, the neutral current is 0 and therefore its impedance is not included in the calculation of the voltage drop and power loss. Let us compare the voltage drop and power losses of a double-phase 2 wires ungrounded system with those of an equivalent three-phase system. This figure shows the two-phase system, where the voltage equals square root 3 times the source phase voltage. The power delivered by the system equals the voltage VLL times the line current, that equals also square root 3 times source phase voltage times the current. Now, if we consider delivering the same power through a balanced three-phase system as shown in this figure, then the total power can be expressed as shown in this equation. Since we want to distribute the same power over the two systems, we can deduce that the relationship between the currents in both systems are related by this equation. We can deduce that the relationship between the currents in both systems are related by this equation. The voltage drop in the three-phase lateral can be expressed as given by this equation. And the voltage drop in single-phase lateral is given by this equation, where Kr and Kx are conversion constants of R and X and are used to convert them from their three-phase values to the equivalent single-phase values. These are usually approximated as follows. Kr equals 2. Kx equals 2 when underground cable is used, and Kx nearly equals 2 when overhead line is used, with approximately a plus or minus 10% accuracy. So we can write the voltage drop in the two-phase circuit as given by this equation. Therefore, calculating the ratio of the voltage drops, we can say that the voltage drop in the single-phase ungrounded lateral is approximately 3.46 times larger than the one in the equivalent three-phase lateral. Since base voltages for the two-phase and three-phase laterals are expressed as follows, as functions of the source phase voltage, we can obtain that per unit voltage drop in the double-phase ungrounded lateral is twice larger than the one in the equivalent three-phase lateral. On the other hand, the power losses due to the load currents in the conductors, of the single-phase lateral, and the equivalent three-phase lateral are. Since the currents in the two circuits are related by this equation, we can write the double-phase circuit power loss as shown here. Taking the ratio of these two expressions, we can conclude that the power loss due to the load currents in the conductors of the double-phase lateral is twice larger than the one in the equivalent three-phase lateral. Therefore, we can conclude that, by changing a double-phase lateral to an equivalent three-phase lateral, both the per unit voltage drop and the power loss, due to copper losses in the primary line, are approximately halved. Now, let us compare the voltage drop and power losses of a single-phase two wires ungrounded neutral system with those of an equivalent three-phase system. The power transferred by the single-phase system is given by this equation, and the power transferred by the three-phase system is given by this equation. Equating the two power equations, we can find this relation between the single-phase circuit current and the three-phase circuit current, which demonstrates that, the current in the single-phase lateral, is 3 times larger than the one in the equivalent three-phase lateral. Therefore, we can express the voltage drop in the single-phase circuit as shown in this equation, which leads to concluding that, the voltage drop in the single-phase ungrounded lateral, is approximately 6 times larger than, the one in the equivalent three-phase lateral. Now, comparing the power losses in the two circuits, and considering their currents relation, we can conclude that, the power loss due to the load currents in the conductors, of the single-phase lateral, is 6 times larger than, the one in the equivalent three-phase lateral. It is clear that, upgrading an existing single-phase distribution lateral into a three-phase lateral, will increase the power transfer capability, and decrease significantly the voltage drop and power loss. This is the end of this lecture. I hope that it was clear and informative. Thank you for watching.